Okay, let's talk about soils and erosion and weathering and sedimentary. Okay, we were talking about the idea that weathering was the breakdown of the rock, erosion was carrying those particles away, sorting them out, redepositing them somewhere else. And these are kind of cool little things that you see once in a while. And basically, it's the same rock, but look at the holes that have weathered into it. It doesn't take much to start with a little pit and see that preferentially grow to a bigger and bigger hole on the surface of the rock. Water is one of the key ingredients for weathering rock. So any place that I can hold the water on the rock a little longer, I can help speed up those chemical reactions a little longer. And even though it's just a little here, a little there, remember our theory of uniformitarianism, it all adds up. So what we're seeing is just this differential weathering where these little lows on the surface of the rock held the water a little longer and they're simply developing these pits. Conversely, the mineralogy makes a difference. Here you can see a softer matrix surrounding a harder pebble of rock, a little piece of xenolith in an igneous rock. And the igneous rock is weathering faster than the xenolith. So composition, the original parent material counts. And here again you can see how these pits can start to grow together as they continue. And here you see a little dike of apatite in the igneous rock. This even works on a vertical surface. It's pretty obvious, I think, that a horizontal surface would hold water a little more. But even on a vertical surface, once you get a little bump started, in the bottom of the bump, you can hold just a little bit of water, and you start developing these honeycomb kind of structures in the weathering pattern. And they're really pretty spectacular. You don't see them very often, but it's just differential weathering. So, remember we looked at those spheroidal weathering, big giant boulders last time? And they're produced by what? Mechanical weathering, chemical weathering, A and B, all of the above. Or none of the above. What do you think? I'll give you 15 seconds.
It's not going.
Not like to work. No, it has some batteries. Something else is going on here. My clicker gets used a lot more than yours.
That's what I do when I get mad.
Okay. Let's see how we all did. Looks like everybody got it right to some extent. C, all of the above. It's both mechanical and chemical. If you remember, we start out by mechanically fracturing the rock to kind of give it some pathways now to start working along. And then we chemically start to attack the corners of those blocks at a faster rate than the sides of the block. Corners we can hit from 3 sides, right? Face we can only do from 1 side. So the chances are we're going to get that corner knocked off pretty fast.
Now I understand.
And now you can see this person for scale. Pretty spectacular boulders that we end up with. Okay, so what controls all this weathering and erosion? And basically, we've already kind of looked at a few of these things, this idea of the parent material. How stable are the minerals at the surface of Earth? And how fast are they going to weather? Obviously, more unstable things are, the faster it's going to go. Climate. This is a biggie because this is temperature and water. Vegetation. Now we're talking stability and nutrients. And topography, well, it's residence time. In other words, if I have a flat layer and I put water on it, that water is just gonna sit there. If I have a steep slope, that water is gonna run right off. Short residence, not very effective. And time, this is the tricky part. So we're just gonna step through these one at a time here, talk about them a little bit, so you'll have plenty of opportunity to write these down. Remember old Buddy, the Bones reaction series here? And it simply was showing the stability or the crystallization